Hey guys, hope everybody's doing okay. What we're going to do today is look at our first lesson in a short series on titration curves. So we're relatively familiar with the titration and how we go about doing that, but what we could do during a titration is actually keep track of our pH. So if we're combining a strong acid and a strong base, like in the upper left-hand corner of the screen here, we could see what is our initial pH level, and how does our pH level change throughout the titration until we reach like the very, very end of our titration. Now in class, whenever we did our titration, we didn't really keep track of the pH. We would stop once we hit the equivalence point. Okay, and our phenolphthalein indicator would have told us where that was. But every titration curve looks a little bit different depending on what you are combining, whether it's a strong acid or a strong base or a weak acid and a weak base or some combination of those things. Depending on what you're adding together, your pH curve is going to look a little bit different. So we're going to look at a couple different scenarios throughout the next couple lessons. We're going to start today, though, with strong acid, strong base titration. So let's take a look at how that works. So the first example in your notes is to combine a strong acid. In this case, we're going to combine hydrochloric acid, HCl, with a strong base, NaOH. All right, so HCl is one of our 7 strong, and NaOH is a strong base because it's a group 1 metal combined with hydroxide. So let's write the balanced chemical equation for the reaction between these two things, and then we'll take it from there. So our strong acid is HCl plus NaOH. This is a classic double replacement neutralization reaction. So your hydrogen and sodium ions will switch, and we're going to end up with NaCl and water. Okay, so what we want to do now is look at just look at our products here. What are we left with in this chemical reaction? We're left with water, and water is obviously a neutral substance. Okay, we're also left with sodium chloride, and if you go back to our hydrolysis of salt lesson, sodium, Na, is a neutral cation, and chloride is a neutral anion. So when all is said and done here, when we have just our product left over, at the equivalence point, when we have no reactants left and just product, our pH should be neutral, which is 7. Right? And we're going to see that as we go throughout the lesson today. Okay, so it says, what's the initial pH of the 50 mils of 0.1 molar HCl? So we're going to start with 50 milliliters of 0.10 molar hydrochloric acid. I want my initial pH of that. So if you look at your equation for pH, it's negative log of your hydrogen concentration, right? Hydrochloric acid is a strong acid, right? So it completely dissociates in water. So if you have 0.10 molar hydrochloric acid to start with, that will fully dissociate, and you'll have 0.10 molar hydrogen and 0.10 molar chloride. Okay? So what's the concentration of your hydrogen ion? Well, it's easy because it's a strong acid, completely dissociates, so we have negative log of 0.10 molar. Okay? Pop it in your calculator, or maybe you don't really need to here. You should know these basic conversions here with your logarithms. You get a pH of 1. All right, so our pH of 1 is where our titration curve is starting. This is before we add any base to it at all. Obviously, as we add base to it, our pH is going to go up because the higher your pH, the more basic it is. So as we add sodium hydroxide, we have less hydrochloric acid, right? We're taking the hydrogen out of solution, right? And we're turning it into, it's combining with hydroxide to make water. So that's why our pH will gradually go up as we add a base to it. So let's go all the way to 49 milliliters. Let's say we add 49 milliliters of 0.10 molar NaOH. All right. So you have your, excuse the drawings here, you have your Erlenmeyer flask. Okay. This has your hydrochloric acid in it. Oops. And you have your burette, okay, with your NaOH in it. All right. You're dispensing NaOH into the hydrochloric acid in your Erlenmeyer. You're going to put 49 milliliters of base from your burette into the Erlenmeyer flask. All right, let's do some math here and figure out what the stoichiometry looks like. So our initial moles, and that's going to be, we're going to focus on moles here for a minute. the initial number of moles of HCl. So we're going to do moles of HCl initial, okay, is what? Well, we had a 0.10 molar HCl solution, right? So let's rewrite that as 0.10 moles per liter. Okay, this is just a simple Chem 1 conversion here. And I had 50 milliliters of it. So I'm going to multiply that by 0.0500 liters. Okay, my initial moles of acid is going to be 0.0050. Okay, that's how much acid I initially had. Okay, now let's look at the number of moles of NaOH I added to it. Okay, so I added 49 mils of 0.10 molar. So this is going to be the moles of NaOH that I added. Okay, so I had a 0.10 molar solution, 0.10 moles per liter, times 0.0490. 0.0490. Okay, that's how many milliliters, well, that's how many liters I added. 49 milliliters is 0.0490 liters. So I added, I mean, this isn't really hard math here, I added 0.0049 moles. So this is important. I started with 0.0050 moles of acid. I added 0.0049 moles of base. Okay, so it combines, if you go back to your chemical equation here, it combines in a 1-to-1 ratio. All right, 1 mole of NaOH will react with 1 mole of hydrochloric acid. So if I started with 0.0050 moles of hydrochloric acid, I added 0.0049 moles of base, I'll have a little bit of acid left over. So let's find the moles of excess HCl. Well, that's simple. We have 0.0050 moles of HCl minus 0.0049 moles of NaOH gives me an excess of 0.0001 moles of HCl. Okay, that's how much HCl I have. That's how many moles of HCl I have left over in my flask. Okay, my total volume of solution in my flask now. Remember, I had 50 mils of HCl to start. I added 49 milliliters of NaOH. That gives me 99 milliliters of solution so far, or 0.099 liters. All right. So what I want to do now is figure out what's my hydrogen concentration. I want to know what my pH level is at this point in my titration. Okay, we're going to compare it to what the pH level was to start with. So if I have 0.0001 moles of HCl left over, that means my hydrogen concentration is moles per liter, right? Moles of hydrogen per liter of solution. Remember, HCl still completely dissociates, so if I have 0.0001 moles of HCl, that's how many moles of hydrogen I have. 0.0001 moles of H plus over my volume of solution, which is 0.099 liters, gives me a hydrogen concentration of 0.001 molar. My pH then is negative log of that, right? So negative log of 0.001 equals 3. Okay? So look at that. It's really neat. After 49 milliliters of base, I'm 1 milliliter shy of my completely neutral solution there. After 49 milliliters, my pH level went from 1 to 3. So let's look at, if we actually plotted this on a curve, you guys have this on the next page or two of your notes, so you take any notes on it that you want here. We started here, okay, with just our acid, H plus and Cl minus. You can see that in the picture representation here. And when we're back in class, I could show you this on the board. we added some base. Here's our NaOH. We're adding base to it. The chemical reaction that we have here is occurring. Okay? And we eventually get to right here where this circle is. That's your 49 milliliters, approximately, of base that you added. And look, our pH went from 1 to 3. So very, very, very small change in pH at this point. Okay? Let's take a look at what happens when we add 1 more milliliter. All right? So let's add 1 more milliliter of NaOH. So we're at 50 milliliters of it. Okay? 50 mils of 0.1, that should be molar. Okay? 50 milliliters of 0.1 molar NaOH has been added to the flask. So if you do the math from the previous slide, I'm not going to do it all over again. We added 0.0050 moles of NaOH, and our initial molarity of HCl was, or moles of HCl was 0.0050. So we've added exactly the same amount of moles, that's key, moles of base and acid. That is called the equivalence point. All right? And that's what we're trying to reach during our titrations. That's when we would have stopped with our indicator changing color in the ones we did in class. So we're at the equivalence point now, and the key thing here is at the equivalence point, moles of acid, moles of base are equal. All right? In this case, the pH is 7, because if you go back to what we had initially, oops, here we go. Our products, okay, because at the equivalence point we have just product, and that's going to be on that slide I'll go back to in a second. Our products are all neutral here. Okay? Water's neutral, NaCl is a neutral salt, so that's why it's really important to know that hydrolysis of salts lesson from a couple lessons ago. Titration curves bring in a ton of different concepts from throughout the unit, and it all just builds. All right? So right here it says we have just product left, water and NaCl, which are both neutral, giving us the pH of 7 at the equivalence point of a strong acid, strong base titration. So if I go back one more time to the very first slide of today, you can see that any strong acid, strong base titration is going to have a pH of 7 at the equivalence point, because we're going to be left with a neutral solution at the end, a water and a neutral salt. Some of the other lessons that we'll go through a little bit later, it doesn't happen. All right, so here we are. We're at this part. pH of 7. We have just product. You can see the water isn't written here to show it, like to show it in a simpler form. You have just Na and Cl ions in there, which are your neutral ions. Okay, well, let's wrap it up here with the last little situation. So let's go one step further than the equivalence point. Usually, we usually don't do this because we haven't plotted the titration curves in class. Maybe we will, depending on what year it is. But let's add 1 extra milliliter of base and do the stoichiometry again. All right. So some of this we don't need to recalculate because the initial moles of HCl we had already. The initial moles of HCl is what we started with, and we already calculated that a couple slides ago. 0.0050 moles. Now we added 51 milliliters of 0.1 molar NaOH. So let's see how many moles of NaOH we added. Okay, the moles of NaOH that we added here is going to be same calculation as last time. We have 0.10 moles per liter, so it's a 0.10 molar solution, times 0.0510 liters. Okay, so we added 51 milliliters, that is 0.0510 liters, and the moles of base that we added is 0.0051. Okay, so imagine you doing this. You had 50 milliliters of 0.1 molar hydrochloric acid. Now you added 51 milliliters of 0.10 molar base to it. So look, we have an excess now of base, right? The first go around here when we had 49 milliliters of NaOH added, we had an excess of acid, right? Because we had to add 1 more milliliter to reach the equivalence point. Now we're past the equivalence point, so we have excess base. So note that on your note sheet it says moles of excess NaOH. That's really important. So moles of excess NaOH is simple. You have 0.0051 moles of NaOH minus 0.0050 moles of HCl. Gives us an excess of 0.0001 moles NaOH. The first example, we had 0.0001 moles of HCl as our excess. All right, so let's go through and finish the rest of this. The total volume of solution, we had 50 mils of acid to start with. We added 51 milliliters of base. So we're at 101 milliliters, which is 0.101 liters of solution. Okay, and let's go through and find our new pH level for this. So we have excess NaOH, so I'm going to find the hydroxide concentration instead. Okay, so this is our lesson on pH and pOH, all coming back here and using it for another lesson on titration curves. So the concentration of hydroxide is 0.0001 moles over 0.101 liters. And that gives me 0.00099 molarity, okay, molar hydroxide. So how do I find the pH? Well, I need to find the pOH first because I have my hydroxide concentration. And there's a relationship between that, right? So I'll review it here. So we're going to find our pOH first. pOH is negative log of your hydroxide concentration. See if I can fit this all in here, which is negative log of 0.00099. And that's going to give me approximately 3 for my pOH. All right, my pH then is 14 minus my pOH from that lesson. 14 minus 3 is 11. Okay, so my pH is 11. So this is really neat because in a span of 2 milliliters, we went from back here, okay, when we had 49 milliliters of base, our pH was 3. We added 2 more milliliters. That's it. And look what happened. Our pH jumped to 11. That's why it's so important when you're titrating to go really slow by that equivalence point. Because if you don't, like if you're off by 1 or 2 milliliters, you just changed 8 pH levels in 2 milliliters. So that's why those half drops or those like 360 flips are really important to go really slow when you near that equivalence point. So here we go. This is when we had excess acid down here at the bottom of our titration curve. We reached the equivalence point right here when moles of acid and moles of base are exactly equal, and our pH for a strong acid, strong base is at 7. And then as soon as we have excess base, because look at the picture here, as we add more NaOH, there's nothing left for it to react with. Sorry to go back a million times to this equation here. There's no other way to do it. Once all the hydrochloric acid has reacted, okay, and you're just adding base, there's nothing for the NaOH to react with. So the hydroxide ions, because this dissociates, the hydroxide ions stay in solution, and hydroxide is a base, which makes your pH go up more and more. All right, so that's why after your equivalence point, the pH is obviously basic, and it continues to be more basic because the hydroxide ions are now in solution with nothing to react with. And we'll see that right here. Okay, so there are your hydroxide ions the more and more you add. Eventually you would just keep adding base until your pH went pretty high, obviously. All right, so again, as you're plotting your titration curve here, you're starting with a very low pH because let's say we're starting with an acid. You're adding your NaOH. You add it a little bit at a time. You near your equivalence point, you add it some smaller intervals, and look, such a sharp rise here to reach your equivalence point, and then it gradually flattens out again. All right, so the key thing here is your equivalence point is 7 for a strong acid, strong base titration. You can use different indicators. We're used to using phenolphthalein, so right after that equivalence point, it will change color on us. That's why we want to have that light pink color about right here. And you can pick some different indicators like methyl red. They change at different places though. So you want to make sure you pick an indicator that changes color where you want it to. We'll talk more about indicators in a different lesson. Okay, guys, that's part 1 of this. We'll go through some other parts in some future lessons. All right, if you have any questions, let me know. That's it. Thanks, guys.